Okay, we're going to close this section 12.1 here today. We've been talking in this chapter about different inferences that we can draw on the slope of a regression line. Spent much of our time discussing how to make a confidence interval to try to figure out the location of the true population slope, comparing two variables from a regression. And now we're just going to shift to testing a hypothesis running significance tests regarding the slope. And so again, slopes generally tell you whether there's really an association taking place between your two variables. If your slope's positive versus negative, you do have an association, but if the slope is 0, then there's not really an association or a relationship between your two variables. Okay? So the formula that you're given on the formula sheet for how to get your test statistic for running a significance test generically looks like this. Of course, when we are applying that to calculating the test statistic for these slopes, those variables will get replaced. Specifically, your statistic is your sample slope. The parameter is your hypothesized value from the null hypothesis. Incidentally, this will always be 0, okay? Because the null hypothesis is always a statement of equality, and so we are hypothesizing that there is actually no association at all between the two variables. We collect our data, we run a regression, and we see if the evidence is convincing enough to lead us to our alternative hypothesis, which would generally be a statement of, if the slope's positive, negative, or it could be does not equal to. Now, the denominator is our standard error of our statistic, in this case, the standard error of our slope, and we are still using degrees of freedom n-2. Okay, so there's a lot of computer output with these slope problems here. I guess the one thing that I just want to make sure that, again, we're just kind of comfortable with is our null hypothesis is always saying that beta equals 0, which in essence, that is saying there's no relationship, versus it could be a does not equal to, could be a greater than, could be a less than. That's saying that there is a linear relationship or association between your two variables. Now, here's one thing worth noting. When you're given this computer output data, it is used so much using a does not equal to symbol here in your alternative hypothesis. So the does not equal to is just kind of a general way of saying that there is some type of relationship or association between the two variables. We're not necessarily suggesting whether it's positive or negative, but it's one of those two. So there is a relationship, and it's used so frequently. Obviously, we know that's a two-sided alternative hypothesis. It's so common that most of your computer output is calculated as a two-sided test. Okay? Now, what that means is the p-value that you're given in the computer output, and I'll just highlight it right here, that is the p-value from having ran the test. We haven't talked about that yet, but that's actually what that number represents. That if your particular test that you're running was a one-sided test, a less than or an equal or a greater than in your alternative hypothesis, what you would need to do from the computer output is you would need to take that p-value and you would need to essentially cut it in half. Okay, one second, I'm having some issues with my marker here. Let's see. So let me register. Okay. So right here, you're going to cut that p-value that I highlighted there in half if the test you're running is a one-sided or one-tailed test. Assume the computer output is always showing you a p-value as if it were a two-sided test. So this is the computer output that we are going to use for this example here, example 3, which is talking about how tipping takes place at a buffet. It says, do customers who stay longer at buffets give larger tips? And so I want to just draw your attention to these directional words here. Staying longer, giving larger tips. Okay, so Charlotte, an AP Stat student who worked at an Asian buffet, decided to investigate this question for her second semester project. While she was doing her job as a hostess, she obtained a random sample of receipts, which included the length of time in minutes that the party was in the restaurant and the amount of the tip in dollars. Here are the data, along with some output from a least squares regression analysis. So you can see we've got some information. Oh, I guess this is the computer output, not this data up here for this particular problem. Okay. Now let's look at what the question is here. The question is saying, does this data provide convincing evidence of a positive linear relationship between the amount of time and the amount of tip for customers at this Asian buffet? Okay. So we know the phrase convincing evidence means we should be running a significance test. Thank goodness, again, we see this a lot. It just says assume that the conditions are met. So when we get to the A in the phantoms process here, that's where we list our assumptions or conditions. We're just going to make a remark that we are assuming that they've been met. So the P in phantoms, this is where we would define what our parameter is, beta. This is what the claim is being made about, the true population slope of the regression line relating, we can say in context, what our two variables are: time spent at restaurant and tip amount. Those are our two variables. All right, then we're going to draft our null and alternative hypotheses. Okay. The null will be suggesting that the slope, in fact, of these two variables is 0, meaning that the line itself is horizontal and there is really no relationship between the amount of time spent and the tip. Now, I put in a box up here in the problem that we're looking to see if the convincing evidence is pointing in the direction towards a positive linear relationship. If it's a positive linear relationship, that means the slope would be positive. Therefore, we're going to say that beta is greater than 0 for our alternative hypothesis. And we're just going to stick with default alpha level of 0.05 since they did not define that here in the problem. I'm going to go ahead and list that we are going to assume conditions have been met. Right. And the N, here's where we're going to name this particular test. Okay, you have two options, two different ways to name this. This can be called a linear regression T. It's a test now, not an interval. Okay, or you could call it a T-test for slope. We always use T-scores for slopes and means, and Z-scores for proportions. Okay, so now we're going to calculate the value of that T-score here. Okay, we know that the formula that was at the very top of this notes page said to take the statistic minus the hypothesized value divided by the standard error of the slope. Now let's look back up here at our computer output. Okay, the statistic is the sample slope. That would be this number here. That's our B. The standard error of the slope, that would be this value right here. Okay. And of course, the hypothesized value, that's a 0. Okay, that's always a 0 because we're saying that there is no association between the two variables. Okay. So I'm going to go ahead and plug those in here. 0 goes here. Now that gives me a T-score of 1.23. Now I want to point something out here. This is really great. In this computer output, do you see how this column is titled T, and then this column over here is titled P? We are in the slope column, or slope row, that's the second row here. You see how it says the T is 1.23? That is exactly what we got right here for our T-score. It is also actually reporting what the p-value is there. Okay, now, we do have to be a little bit careful before I write that down here. Okay, remember, all these computer outputs are assuming that they ran the data as if it was a two-tailed test. We know this is definitely a one-tailed test. I'm getting that because right here we chose a greater than symbol. So that p-value that I'm going to grab right here is actually representing the area in both of the tails. So I'm going to need to take that area and I'm going to need to divide it by 2 so that I'm just getting the area for one tail. This is what I would use for the p-value. Now, I was able to grab most of that information from the computer output. I technically would not have had to have shown that calculation, but you do need to report always the degrees of freedom. You can see in the table, there's 12 sets of data. So somewhere on your paper, you need to have written down that the degrees of freedom are 10. Okay, then we're just going to fill in these blanks here. Since the p-value, remember that's cut in half, 0.124 is, let's see, greater than the alpha level of 0.05, that's going to cause us to fail to reject the null hypothesis. We are going to say that we do not have convincing evidence that, and then I drafted essentially what the alternative hypothesis is, that the customers who stay longer leave bigger tips. Okay, now, how I knew to say that is because if the slope really is positive, then that's what that means. As your x variable goes up, your y variable goes up. That's what a positive association means. Okay, and that's what our alternative hypothesis was. So I'm saying that in the context that I don't have evidence that the slope is positive, which means as the customers stay longer, they tend to leave bigger tips. There's not evidence in support of that. Okay, not going to do the next example, although I do want to share with you the feature on the calculator, but I think that you'll find that when they give you the computer output, that's even faster than doing it on the calculator, because doing it on the calculator requires that you've typed in like all the data into L1 and L2. So again, you would have to put the data into your list. You would first have to run a linear regression, and then you would perform your inference procedure on the calculator. So again, how that would look on the calculator is you would go to stat, test, at the bottom. Now make sure you're picking linear regression t-test, not linear regression t-int. And then you would identify that your data is in L1, L2, and then come down here and pick which directional symbol your alternative hypothesis was in. Does not equal to, less than, or greater than. Okay, and it will report for you then, of course, the t-test statistic, and it will also report the p-value. And when you do it on the calculator, you know, if it's a one-tailed test and you're specifically saying what that is, you don't need to be dividing the p-value in half. You only have to do that if it's given to you as computer output. Then you should assume that the p-value that you're seeing there represents area in both tails. Okay, I just underlined here again that phrase where a lot of times, watch for that. If the conditions are met, you don't have to do that whole liner acronym of running through those 5 conditions. We're going to skip that example. We're just going to take a look at this very last example here at the bottom, at the back, where this is talking about infants who cry easily might be more easily stimulated than others. So this could be a sign of higher IQ. Child development researchers explored the relationship, here's what they're the 2 variables, between crying of infants 4 to 10 days old and their later IQ test scores. Okay, snap of a rubber band on the sole of the foot, oh, that's so sad, caused the infants to cry. The researchers recorded the crying and measured its intensity by the number of peaks in the most active 20 seconds. They later measured the children's IQ at age 3 years using the Stanford-Binet IQ test, and a scatter plot and mini output for the data from a random sample of 38 infants is given below. Assume all the conditions have been checked. Here we go. Does the data provide convincing evidence? We're going to run a significance test of a positive linear relationship. That means my alternative hypothesis is going to look like that. beta is greater than 0. Between crime count and IQ in the population of infants. Right. I think I had blanks for this, possibly for you to fill in, maybe on your notes page here. Okay. The name that we would fill in for this, I'm just going to go through a few of these here. The name would be linear regression t-test. Our hypotheses, I'm kind of doing this in a weird order here. It would be that. We're going to do an alpha level of 0.05. We are going to assumed that those conditions here are assuming that those conditions are met. Okay, and I'll come back here and just define this as beta is the true population slope of the regression line relating, here's our two variables here, cry counts and IQ at age 3. Okay, so I need the t-score. I should be able to just grab the t-score. That's my test statistic right from the computer output. Oops. So I'm going to go ahead. Oh, gee. Keeps jumping. Right here is the t-score, and this is the p-value, but this is the p-value for a two-tailed test. This is also not a two-tailed test. We're going to need to cut that in half when we report it. So 3.07 is our t-score. I'll need to write down the degrees of freedom. The p-value is going to be that number from the computer output cut in half. Okay, degrees of freedom for this. Let's see here. We had 38 infants, so that's going to be 38 minus 2 degrees of freedom, 36. Okay, our p-value of 0.002, definitely less than the alpha level. So we're going to reject the null hypothesis. Now we're going to say that we actually have convincing evidence that there is a positive linear relationship between crime counts and IQ in the population of infants. That means as the crime counts went up, their IQ would go up as a 3-year-old did. Okay. All right, I think that brings this section here to a close. You can see at the bottom of your page there are a few problems for you to go ahead and try with significance tests.